Okay.
So,
what are you going to talk about?
My name is Guilherme. I will talk about data frames. So this is the title. I decided to keep the same title as it was before. Okay, so the outline of the talk is we define the problem we're trying to solve, talk about the greatness of T-data frame, show some performance figures, and do a little diversion before we go. I recommend looking at the talk on Thursday by Jacob. He will make some comparisons and show some extra performance figures from T-data frame when looking over data. So I think everybody knows the drill by now. We will have a lot more data to process and not as many computers to process them. So we need to improve our software to be faster, to take advantage of parallelism. So I've not spent too much time here. So this is a challenge and an opportunity. So we need to improve our software. But we also have the opportunity here, I cannot emphasize enough, we need an easier programming model. We want to make the computer run the software faster, and we want to make the physicists write the software faster also. So to obtain more results with less effort. This has been proposed or announced at CHEP. I wasn't there. So this is what I'm presenting today is the evolution of this. So you can see here you have this filter and then map and cache and filter and so on. So now I'm going to show T-data frame. It's a declarative approach to data analysis in root. It's basically the comfort of the big data tools, but with the speed of root. And Jacob will talk about this speed. And it's available since root 6.10, released in June this year. So it's a new way to interact with root columnar data format. It took inspiration from things like Pandas and Spark, and similar ideas shown by our very valuable Windows customer at the Amsterdam workshop. I also wasn't there, but I watched it via video. So in this framework, the analysis is a graph of transformations and actions. So transformations can be a filter. You can define a new column to add temporality to your data. And then the action is to just fill a histogram or create a profile or you count your events, take the mean, and so on. So it's a very different way than people usually do, where you specify what you want, and then you let root choose for you how it will get done. And this allows the computation of the event loop to be done lazily. And you have several opportunities for optimizations because the loop is under control of T-data frame. So you have partitioning, caching, parallelization very easily. So here's the basic example. It's just less boilerplate code. With T3 reader, you create your T3 reader values, you do a while loop, and if your event is passing your filters, you fill your histogram, and then if you have 10 other histograms, maybe you will do another loop there. Then this loop is in Python. It can be slow, so not very easily to parallelize this loop. So if you look at how you do this in T-data frame, you create a T-data frame from your tree, and you just create your histogram from filtering your data with the same filter function and creating an action. So you do a transformation and an action, and you have a histogram, and here you draw the histogram. And then at the point you draw the histogram, the loop executes, and you used a lot less lines of code to do the same operation that you did with the T3 reader. Another thing is parallelization in this model is trivial. You add this, enable implicit MT, and the other part, this is the same. Don't have to change. So it's really parallelism at the reach of anyone. And when you call root enable implicit MT, you're not only parallelizing the T-data frame internal operations, but if you have 100 branches, you also parallelize root I/O, for example, and other areas of root that support implicit parallelization. So the other key point is the ease of use. So you have very simple programming model, reduce boilerplate code to a minimum, and you can also write simple code because we have clean. So instead of, so if I'm doing a histogram, you can create a T81F or T81D. So you would have to specify this if we had to write valid C++ code, because the data frame is heavily templated. So it takes all the complexity for itself and lets the physicists write very simple code. And then when you call this function, then some magic happens inside that checks this column, says, oh, it's float. So it does this just-in-time compilation for you. So instead of having to write this sort of thing, you just write this. V1 times V2, you define a new branch, or you define your PT from other variables and so on. So it makes it much simpler. And here you use the string is not a domain-specific language, it's just C++. When you call this, your Kling will just-in-time compile the code for you, and you can have type safety and everything. So here's the simple example of minimal analysis, creating the T-data frame. Then you attach two different filters. So you create sort of a chain of things that you want to be done. And then for each filter, you also add a histogram, and then you can draw the histograms. And you're not running the loop twice to draw the two histograms. Once you call the first draw, the event loop runs, but it also computed this other one. So you don't need to rerun the whole loop there. You describe all of the things that you want to do, and then at the end, everything gets done for you. But it's not just a chain, it's really a graph. Because if you pick from some point the data frame, so you create a data frame, then you filter it and define a new column. So you go from this, which is the first data frame, you create a filter, then you create a column, then you can attach the actions. But I could very well just create a different filter here, attach more things. So you can create a graph of your analysis and do several variations of the same thing to run everything in the same loop. Finally, T-data frame introduced a new way of writing trees using the T-buffer merger internally, as Axel mentioned. So it's very easy to just read some file. You do some filtering, then you define columns, and because you don't want to keep defining this every time, you can just call snapshot, and then you give the tree name and the file name, and choose the branches that you want to save, and it gets written to you. Gets running parallel. The branch is computed on the fly, and at the end, it's saved in parallel, merged into a single file at the end. So I will mention this in the talk on Thursday. One thing that is not here, but it's also possible, is say I want to do some exploration using Pythia. I don't have data file, but I know the model that I want to use. So you can create an empty data file. You say, I want 10,000 events. Then you create a branch that calls into Pythia. And then every time when you do the loop, it will call Pythia, get an event, and then a few histograms based on that. And then that's, if you're limited by I/O, this could be a way to scale up in an easier way. So here is a list of some of the transformations you have and the actions. So you have defined new columns. You can filter by some user-defined function. You can pick up a range. So if I have a terabyte, I don't want to run over the terabyte to do some simple pre-checks on the cuts that I'm applying. And then you have the actions. You have histograms, min, max, min, profile, reduce with the user-defined function, and the snapshot. And I recommend anyone interested to look at the online documentation. Everything is in there on the root website. So now I show some performance figures. This is a conversion into T-data frame of a WMS analysis. Thanks to Mark Dunster for that. So Danilo ran this on a server with 32 logical cores, with a 2.5 gigabyte input file, and filling 1,100 histograms, 3D histograms. And the times here include even the merging of histograms. And on this machine with 16 cores, you can see that when you enable implicit parallelism, you have a 12 times speed up. And even with hyperthreading, you get a little more. So it's not so bad scaling for one line change. So here, it's a performance figure for throughput on event processing, reading data in root format. And so here you have a root with a regular approach with set branch to DAS. Here you have T3 reader and T-data frame. There is a little bit of overhead compared to the T3 reader, which it uses internally. But it's mostly due to filters, and it's being optimized. Enrico is working on it. But you can see that, again, with the same one-line change, you get some speed up. And this is in a laptop with 4 physical cores, 8 logical. In the compression, this overhead is less significant, and it's still good speed up when you enable implicit MT. So a little diversion now. We wanted to mention that so this is all in a single machine. If you want to scale to multiple nodes, there is also work going on with dist root. So it's to minimal interface for map reduce pattern to process T3s using PyRoot and PySpark. You define your map and reduce functions, and it relies on shared file systems on driver and worker nodes. I think a previous talk mentioned also this work, and there's work ongoing also by a summer student on monitoring and integration with Swan. So you will be able to log in Swan and use notebooks to launch these jobs and monitor them via this interface. So the bottom line, root now supports T-data frame, declarative analysis in C++. You can use all of this from Python. There are a few things that still need to be adjusted due to templating and so on, but for the most part, it's supported from Python. You can just import root and use it. Same results, just less lines of code, less boilerplate, more efficient for physicists. Very easy to parallelize. Just add one line, and root will enable implicit MT and parallelize it for you. You can use it to extend your data sets very easily, or just use Pythia to write new data sets entirely. And you have distributed analysis with PyRoot and Spark. Will be available in Swan. And for the next release, we'll have a sprint to add more new features. Provide adapters to use T-data frame not only with files in root file format, but also some variations and other formats entirely, CSV and Parquet. Improve the integration with PyRoot, because everybody wants to use Python, and this is a very good way of analyzing data using root in Python, and refine the performance of parallel writing. And that's it. That's what I had to say.
First, we're going to do the math of the questions, and then we'll reduce. You're going to take all the questions at once, process them in parallel, and then answer everyone.
Okay.
Okay.
So you just want me to list my questions?
Yes.
Okay, so two things. So first of all, during the plenary, or maybe it was the previous track 1 parallel session, there was talk about a new way of, during the parallel session, track 1 earlier today, accessing the data directly, so avoiding a lot of the root overhead, just basically getting straight access to the data. It's currently an experimental interface that's going into root. No, by the way, yeah, there he is. Are there plans? From Jim's presentation, it looks like there are significant speed ups using this, or there are plans to try and.
This bulk I/O, you mean?
Yeah, I guess I don't know what the name of it.
Yes.
Bulk I/O, yes. Yeah.
Definitely, this implementation of CD-frame uses T3 reader inside.
Yeah.
But if there are big gains to be had by moving to this bulk I/O interface, definitely that's something that
looks to me like you could do that without the person who was writing the analysis code really having to care, which is of course part of the point of the whole design.
Yeah, in this case, let's say somebody wrote their analysis using CD-frame, but then later we decide to move to bulk I/O. They would not have to change their code. They would not have to care.
Okay, and then I just a quick comment. So everybody is talking about Apache Spark, which is awesome. But my impression is it basically takes a combination of some form of perhaps a data center and somebody who is pretty dedicated to managing the cluster. So smaller universities, which say have a couple of hundred cores or something like that, and it's managed ad hoc. My impression is they have a good deal of difficulty setting up Spark. I wonder if it could be my impressions are wrong, but I also wonder if there's something more lightweight that could also be adapted for doing some of this distributed analysis, say with root.
What would you have in mind?
I have no idea. I have no idea what I have in mind. I'm just
MPI?
Maybe some sort of parallel root facility.
I'm sorry? No. The management headaches and the stability of that were definitely an issue. But I'm sure there must be some distributed job things that are open source that are lighter weight, or maybe Spark comes Dockerized so that if one wants to use it, it's a fairly trivial thing to use. You don't have to worry about the mess, but I just don't know what the answer is. It's just from everybody I've talked to about Spark, for example, it looks like that's not the right answer for the small one.
So Gordon, we have a problem there, and I don't think that the routine is, at least currently, doesn't have the resources to answer this. Because what we've learned from Cruise and from Spark actually is that one of our biggest problems is what happens if your code goes belly up.
Yeah.
Right? And debugging this is a nightmare in a distributed system.
Right.
And Spark doesn't know how to address this, and Cruise didn't really know how to address it. Right? So now basically we have the knowledge of what we need, and we could actually create something. It's not the scheduling. The scheduling is trivia, right? There are many
Great. Give me, because my problem with proof was communications failures, even on a high quality network. Right? Spark, it looks to me like if I want to get that running on my cluster back at UW, I need to task somebody. That'd be great if I can increase the size of my. I mean, I have these machines, right? I'd like to get them up and running stably. I mean, even to the point where I had a problem of wanting a debugger. I'm not even to the point where the debugger is an issue because. And I realize this is not the answer for root. This seems like a generic problem we have for smaller analysis. So for something big, like when you're at CERN, you can go talk to CERN IT, and they'll do a great job. And if there's any issue, you just send an email, and maybe you have to wait a day, but you don't have to learn the internals. Whereas
you don't have to pay those.
Okay, well, that's because I'm not at CERN. Okay, anyway.
One thing in the Python space is fast.
I think there are a couple of people mentioned that.
Those everything's talking about.
All right, one more question.
So you showed the computation graphs. Are there any restrictions on the graph topology, or could I, for example, do one or a selection of electrons and one of muons and do like a invariant mass of the two, like combine them again and iterate?
Yeah, I think that would be possible. I'm not aware of any restrictions.
Okay.
So you just have to understand that the actions and transformations work a little bit different, but you can combine them to create your.
So you can combine two collections and then iterate them.
Yep. Then you will iterate one for both of the things.
It's getting late, but I don't know. There's two hands. But you, go ahead. Yes.
So they're quite focused on this is something that's really powerfully found us.
Yes. So it's definitely being worked on. It's just that with the way that things are implemented right now, there wasn't a quick solution. For example, if you're iterating over 1 gigabyte, it's easy. You keep it in memory. If you have several terabytes and you want to group, so once there is an answer to how to do it, it will probably be there.
If it's burning, go for it. Yeah.
Yeah, could you show the nice scaling? Here, please. Sorry.
I think the best person to answer would be Enrico. I think if the memory usage is most likely related to the data size. Of course, if you have like 1,000 nodes in the CDD frame, it will take more memory. But most of the memory probably will be the caches for the data.
I mean, it's like if you compile that code and find it out into that library. Right. So we're talking, I don't know, man. Next, that's a problem. Comes to me, we get some brand for you. Yeah.
Okay. All right. Well, can we end there?